So, Silly has been teaching you the following kind of theorems that I think the one theorem Zero taught you is Hall's theorem, right, which is basically that if you have given a bipetite graph A comma B times E, then there exists a matching that saturates A if and only if for all A prime subset of A, size of this is greater than or equal to this, right. Did you also learn Hall's theorem? Yes, no? Okay. So, what does basically it is a derivative of Koenig's theorem. Did you learn Koenig's theorem? Huh? Okay. So, what did Koenig's theorem told us? The Koenig theorem told us that in bipetite graph, minimum vertex cover of G is equal to maximum matching of G. Okay. But why it is called Koenig's theorem? Does anybody knows? Yeah, but like, are there graphs that you are aware of, okay, which is not bipetite and where this property holds? Yeah. So, I mean, give me an example of one such graph, no? I mean, graph which is not bipetite where minimum vertex cover is equal to maximum matching. Okay. So, what he is saying is this, right, and this is a vertex cover, right, and this is a matching. Okay. So, there are larger class of graphs where this property holds, but there are also lots of graphs where this property does not hold. Okay. So, today we are going to talk about, okay. So, in the language of Koenig's theorem, in what can I say? I can say given a graph G, given a graph G, an integer k and an integer k, either G has, right, given a bipetite graph G, an integer k, either G has k independent edges, okay, it is on purpose written like that, or k edges that do not share any endpoint, or there exist k vertices that cover all edges. Okay. Okay. Is that fine? Can I prove from Koenig's theorem? Can I prove this? Either graph has k independent edges, or it has, if it does not have, then in fact, I mean, you can cover with k minus 1 vertex. So, what I give you a graph G, okay. So, either it has k independent edges, or if this statement is not true, then there is just k vertex that covers all the edges, right. So, what is the meaning that the first statement does not hold? The matching is exactly. Yeah, so in particular with k vertices, right. Or there exist k minus 1 vertices that cover all edges. I mean, if you want to be more exact. Yes, tell me.
If k minus 1 size matching is there, so we need to like pick all those vertices. All.
Look at the input now. Look at what does this theorem tells you. In the bipartite graph, there is a vertex cover whose size is equal to maximum matching. If the maximum matching size is upper bounded by k minus 1, then there exists a minimum vertex cover of size at most.
So this G is not bipartite.
Given a bipartite graph G, okay, okay. So is that statement fine? Right? And of course, right, if I change this to, I say don't have a bipartite graph, then what can I say? Then I can only say 2 times k minus 1 vertices that cover all edges, right. So this is slightly an approx version of min max result that we proved, okay. So this is like a min equal to max kind of result we proved, right. So this is an approximate version of min max, right. So what is a min and max? What is a maximization object? You are trying to maximize the independent set of edges, or you want to maximize the matchings. And what is the property of this matching? That they are pairwise vertex disjoint. And what is an objective? Objective is to cover these objects. Now trivially, if look at any covering parameter whose objective is to cover this. Now if I find, I want to say, oh, I want to cover all the edges, and I found these many copies of edges which are pairwise disjoint. Now any covering has to pick at least one vertex from here, at least one vertex from here, at least one vertex from here, at least one vertex from, right, because these are vertex disjoint copies, okay. So number of maximum, like maximum number of pairwise vertex disjoint, this H provides a lower bound on how much I need to cover. So what the question is that, okay, so the question we ask is that, okay, this is max, okay, is covering some function of max, right. So this, you rather think that this is like packing, disjoint copies of packing. This is packing, right. And what is this? This is covering. This is covering and this is packing, right. So packing always provides a lower bound on the size of covering, okay. So now the question is covering function of packing, okay. So this is a general question that we ask in graph theory, okay, and this is a very, very big field, okay. Lots of modern graph theory is devoted to this, and we will see some of the nice things about them, okay. So now when covering is equal to packing, then you get this kind of min max result, right. And but there are very few such results, like you see Koenig's theorem, you see Menger's theorem, right. So between SN to SNT, if I, what is that Menger's theorem? Just look at, for, isn't this either you have k disjoint, like pairwise vertex, internally vertex disjoint paths, or you have k minus 1 vertices that covers all the paths between SNT. So this is another example of covering and packing where it holds with equality, but in general it may not hold with equality. You look very confused, Nidhi.
Could you please repeat this packing and covering?
Look at edges. What I want? I want to pack these edges. So what does a packing means? Packing means, okay, so what is a vertex disjoint packing means? The packing could mean very different things based on whether it's a vertex disjoint packing, edge disjoint packing, or minor packing, whatever. But what is a vertex disjoint packing will mean? Okay, so vertex disjoint packing basically means, okay, it's a partition of vertex at V1, V2, VL, okay, or it's a partition, which means that for all I comma j, Vi intersection Vj is phi, okay, and each of these Vi contains a copy of, suppose vertex disjoint packing of H. I wanted to pack H. So every Vi contains, or every graph, each G contains a copy of H. Okay. So this is what we mean by packing. Now, these are pairwise vertex disjoint copies, and each of them contain H. Now, so this is basically a definition of H packing. What is an H packing? Right. So H packing is partition a vertex set into V1 into L copies, so that each of the pieces contains a copy of H. Right. So if H is an edge, what does it mean? Each of this graph contains this. Now, what is the covering? So we can define H covering. What is an H covering? Okay. So what is an H covering? So given a graph G, okay, find a set S subset of Vg such that G minus S does not have any copy of H, right? They are H free. I cannot. So for if H is edge, what this corresponds to? What is this S? What does it mean? I want to delete set such that my G minus S does not have any copy of H, means it does not have any edge, right? So for example, if I put H equal to triangle, what is the meaning of this? So in H packing, I will have to find vertex sets like that, each of them contains a triangle, right? But they are pairwise vertex disjoint, right? And what is the covering problem? I want to find a minimum number of vertices so that if I delete, the graph does not contain triangle, right? So you can come up with any H of your choice, and you can ask yourself a packing question, and you can ask yourself a covering question. Now notice, so given a graph G, what is the packing number? What is the maximum number of copies a graph contains? What is the covering number of graph? What is the minimum number of vertices I need to destroy all the copies of H? So now notice, because this is pairwise disjoint, right? So any covering must contain one vertex from each of this partition, right? So that provides a lower bound, but maybe picking one may not be enough. So you might have to pick more, right? So with respect to any graph, packing number provides a lower bound on the covering number. And what are we interested in studying? So people are interested in, is packing number is equal to covering number? Is covering number function of packing number, right? So the way it is defined, it is very obvious that, say, H packing number, okay, is less than equal to H covering number, but the question is H covering number upper bounded by function of H packing number, right? That's all that it is, right? So if I put this question in this framework, I give you H, okay, an integer k. What either G has, I want to say, prove something of this nature, either G has, so I give you a graph G and some integer k. It should be true with respect. So either G has packing or k vertex disjoint copies of H, which basically means that the packing number of this graph is at least k, right? Or, okay, or I would like to prove, or f of k vertices that cover all H, right? So these are the kind of general theorem that I want to prove, okay? So you understood the kind of question that we are interested in, okay? Now the very simple argument told us, now I want you to make this, suppose H is triangle, okay? Don't tell Soman, not for you, Sona. Okay, so what do you think? Can I prove something of this nature for H being triangle? At least let's understand the question. H is edge, we know how to do it, but H is triangle. How many of you know how to do it? apply, like don't think too much, Nidhi. Just apply definition. Every triangle is a cycle, but not every cycle is a triangle. So I am only talking with respect to triangle. If you know, keep it to yourself. It's 9:53. I'll give you 2-3 minutes to think about it. Do you know? Okay. May I know your name? What's your name? Ajay. Okay. Same, right. You showed up today?
I have a question.
Yes.
So covering edge means we have.
Not edge. Where is the edge?
No, I'm just covering edge means we have to choose one endpoint. So covering triangle means we have to choose two.
No, I do not know. I have written a definition here.
Okay, got it.
It's written. My definition is written what I expect. What is packing means, what covering means. Okay? I want you to parse. That's important. Sanjay, is it fine? Okay. Satya? Okay. Let's do a packing. Let's do a packing for triangles. Let's do the packing of a triangle. I find, let's do greedy packing of a triangle. At least can you find triangle greed? Can you do a greedy packing of triangle? Yes, Nidhi. So tell me, how will you do greedy packing of a triangle?
Maybe in a graph find any three pair or three.
No. I find that, like, you don't have to give me the. So what is the meaning of greedy packing of a of triangles? Okay. How do you find maximal matching? You start with? Yes. No. You start with an edge, then what you do? So what does that mean? I delete that. I delete the end point of this edge, right, and proceed. That's what I do, right? Right? So what is the end point that I chose? Can that not be part of my B1? That's my first partition, or that's my first part. Okay, so let me do, so how will I do a triangle packing? I choose a triangle if the graph has. So suppose my V1 is basically a triangle. Now it's G minus V1. What should I do again? Again choose a triangle, no? Call this V2. What I do again? Suddenly I will, at some point of time, I left here. So look at that question. What does it tell you? If either I succeed finding k triangles, if I don't succeed finding triangles, then can you say something? How many packings did you do? At most k minus 1. How many vertices are involved in them? Total number of vertices in, so if I delete all these vertices, what is left? There is no triangle, no? Sanjay, is that fine? Okay, my H is click on 57 vertices. Give me something. It's a click on 57 vertices. I'm not asking algorithm. We are doing graph theory. So all I care about is proof of this, right? Is for K57 this is true? Click on 57 vertices. Are you sure, Sally? Or do you think it's wrong? So what does it tell us? Basically, either this statement, if given a graph G and integer k, either this statement is true or this statement, but one of the statement is always true. And I am not even talking about computational question, I am just talking about for K57, can I say something? Kushal? Is that fine? So what will you do for K57? Yes?
So if we follow the similar procedure, the FK will be 57 into K minus 1, but finding a click, readily finding a click of size 57, is that easy job?
I mean, I'm not teaching algorithm. So, computational question I am not taking it, okay. All I want to prove this is a structural theorem, okay Madhumita. Computational question is a very different, yes I can find, look at all 57 vertices, check whether it's a click or not, I can do that. I mean, but let's not go there, that's not what the essence is, okay. What is my V1? Dot dot dot, okay. So now either this process goes, then that's okay, or in some graph where it process doesn't go, if I delete everything here which is like 57 times k minus 1, everything else doesn't contain because our greedy process would not have moved ahead, okay. So was there anything about h here? Did it matter what h we took? If h, I gave you h had size h, graph, I want to pack h, right, who has size h. Does it matter? First, I find h, 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 right. So h, right. So all that matters is the size, not the what structure is, right. So vertex cover, there is nothing about vertex cover that you get 2, right. It's just the size of the obstruction, size of the object that you want to pack that matters, right. So what does this gives you? If I wanted to cover, say triangle, what is a trivial approximation algorithm? Find a triangle, delete it, find a triangle, delete it. What is a factor of approximation for this? Factor 3. Why? Because each of the triangle you must pick one because they are pairwise vertex disjoint, and how much did you take? 3 times a lower bound provided by the packing. So these are trivial approximation algorithm that you get. So this trivial approximation algorithm is not limited to vertex cover, but it is limited, but it applies to every structure that you wanted to hit which has a bounded size, okay. So if the family which I wanted to pack gets fixed, like has one graph or fixed one graph, it is simple. So now let's move forward. Okay, let's make the question a bit more interesting. Okay, so now what I'm saying to you. Okay, so I'm going to give you a family. Okay, a family. So this is family of graphs. Okay. So what I'm trying to tell you now, what is the packing question with respect to F packing will be? Let me tell you what F packing means and what is F covering means. Okay. So what is an F packing means? I want to find the partition such that each of them contains a graph from F, right? Contains a graph from curly F, everyone. Like, because now there are many graphs, so you have to come up with this partitioning. I shouldn't say partitioning because it doesn't covers all the vertices, but like disjoint parts, okay, where each part consists of a graph in my family. So what will be my F covering now? Find a set such that in G minus S does not have any graph in curly F, right? In G minus S does not have any graph in my family. Okay. So for example, let's look at F, okay, and look at, suppose F for example is cycles, it's family of cycles. Okay. Now this family is infinite, right? It has a cycle of length 3, 4, if allow multi edges then 5, anything, right? So now what this question becomes? Now either G has k vertex disjoint cycles, k pairwise vertex disjoint cycles, or I want to prove some f of k vertices that cover all cycles, or in our language, what is, there exists a feedback or there exists a feedback vertex set of size at most f of k. So either in my graph I can find k vertex disjoint, k pairwise vertex disjoint cycle, which means now what will be my greedy algorithm here? Okay, what is my greedy algorithm? Find a cycle. Okay, find a cycle. So I find a cycle, delete it, find a cycle, C2, find a cycle, and when nothing is left is this. Okay, but unfortunately, so if it has a k vertex disjoint cycle, that is great, but now I cannot use this procedure to provide a bound because I don't know what is the length of the cycles you use. Length of the cycle could be root n, n to third, I have absolutely no clue, right? So maybe the better heuristic would have been, heuristic again, is find a shortest cycle, right? This is better, if I have to apply heuristic, among G minus V, find shortest cycle. So like I have several choices for this cycle, among all the cycles that is present in my graph, I am choosing the one which is shortest. But still, even the shortest cycle, I have no upper bound on the length. So I cannot do the way I was doing before for H, where the size of H is bound. But imagine if I told you that I give you family where every graph had size bounded by T, then can I say I give you family, but like up until now I was only considering one graph, but does it matter if I told you that I have a family of graphs where every graph has size at most T? Then it's okay, then I can still put T, because anything obstruction that we will encounter in this had size upper bounded by T, okay? But now I cannot say this, okay? So this becomes extremely interesting, right? So now people will ask, okay, that's very good. What kind of family of graphs we could come up with such that this property holds, right? That I can come up with it.
what you were saying is if the family of graphs is not upper bounded by T, then we cannot have a theorem like that.
No, I am not saying. It's not obvious.
This way does not work.
This particular way doesn't work. That's all that I am saying. I mean, there could be a different way of proving. I am saying this proof strategy does not work. That's all that I am saying. It's very okay. So let me define a notion which is called so what they define is called that H is some family of graphs, right? So in our case H is like cycles, okay, or let's say F, okay. We say F has, I think some, how to write, okay. Okay, I should be on. Okay, we say F has Erdos Posa property if there exists a function f from where to where? From natural number to natural number. And what is the property? Such that for each k in natural number and each g like in all family of graphs, okay, either, okay, let us say, and for and each g, either g has k vertex disjoint, okay, k vertex disjoint subgraphs, each containing a copy of a graph in graph in H, or there exists what? Or there exists a set U subset of Vg of size at most f of k such that in g minus u, okay, there is no copy of subgraph, there is no subgraph isomorphic to 1 in, there is no subgraph in H, okay, that is it. Okay. So, I am going to call that, look at a family of graph, right. I say this family of graph has an Erdos Posa property if I can come up with a function from natural number to natural number which has a following property. Okay. So, given any graph k and g, either I can find k copies from here, or I can find f of k vertices that hits all the copies. So, basically I should be able to prove particular theorem. Okay. So, is the setting clear to all of you?
So here H is F, right?
Huh?
Here H is F, right? What is H?
Okay, fine. F, correct. My mistake. Okay, fine. Okay, so now let's try to prove this for cycles. Is that fine? So, what is known? Let me tell you. Okay. So, this is what we are going to show. Okay. So, what I am going to show, either a graph contains k vertex disjoint cycles, or there exists some order k log k vertices which if we remove from the graph does not have any cycle, or either there exists a k disjoint cycles, or there exists a feedback vertex set of size at most or big O of k log k. Okay. Is that fine? Okay. So, if everything is clear, then let us move to proving this theorem. Suppose if I give you a 3 regular graph, okay. Let me see if, let G be a 3 regular say multigraph, okay. What I mean by multigraph, okay, 3 regular multigraph. Okay, this doesn't write very well. Okay. So, I am asking you, okay, how much is a 3 regular graph? Can you tell me some lower bound and feedback vertex set? Let us see if.
What is a multigraph?
Oh, multigraph. This is a multigraph. This is a multigraph. Like, okay. But when I talk about degree, it's a number of edges which are incident on them. But assume that there are no self loops. I want to see if, so I give you a 3 regular graph. Okay. If you do not want to assume multigraph, that is also fine. But suppose I give you 3 regular graph and I say, what do you think? Can I come with some lower bound on the size of minimum number of vertices that I need to delete in this graph such that the graph does not have any cycle? Okay, let me ask a different question. Can you give me a lower bound for vertex cover in this graph? Say lower bound on vertex cover. Let us see. This is exactly what is happening. I'm sure this is how they show. Okay. That is not a lower bound. When I say lower bound as a function of n, can you tell me? I want to say any 3 regular graph, any vertex cover in 3 regular graph or n vertex must contain at least log n vertices, for example, or root n vertices for something. Can you say something on this statement? That is a graph theory. What? Log n by 2. I understand why you are saying log n by 2. I want as a function of n, which is like say at least polynomial function of n. When I say polynomial function of n, it's like root n will be okay, just like polynomial. N 1/3 will also be okay.
N by 2.
N by 2. Why?
One bound can be like 3n by 20.
3n by 20. Why?
So you see two vertices and like there can be one edge, pick up edge and look into the two neighborhood of that edge.
That's good, but like I want something more trivial. My questions are never difficult.
N by 4.
Why n by 4?
So I pick up vertices by 3 degree 3 vertices by 1, so total 4 vertices go. Then again I pick a degree 3 vertex.
कुछ भी, कुछ भी. But that's okay. That's nice. It's on the way. There are more. Okay, let me. Huh? 3n by 2. Why? It's not upper bound. I want lower bound. 3n by.
That's the maximum number of edges in the graph.
But like, how is that a lower bound?
It's like if you pick 3n by 2, it's definitely
3n by 2 is more than n. But that's not a lower bound. That's an upper bound. Okay. So what I want to tell you is that okay, I have 3n by 2 edges in this graph. Okay. Now here's my vertex cover. This person can eat up how many edges? Excellent. Now you know. Because it's a cubic graph. Every vertex has degree exactly equal to 3. So total number of edges is 3, total sum of degree is this, divide by 2. Hall's theorem, we did it in the first class, 3n by 2 edges. Okay. You can only eat 3, you are like, I put up a tie that everybody comes and only can take 3 objects from here. How many persons do I need so that it becomes empty? Huh? Tell me. By 3x should be at least 2. So x is at least n by 2. So any vertex cover. So what is my statement? If a graph G is 3 regular, then any vertex cover, minimum, maximum doesn't matter, any vertex cover has size at least n over 2. Okay, make such statement for feedback vertex set. I want to see. Huh?
I was saying n by 4 for the feedback vertex set.
Why? I was only asking about vertex cover first. Now that we have done it, I want to understand this.
This bound will hold for
Think, no? And not n by 2. Look, I don't know whether n by 2. I am saying, can I prove similar kind of things, right, for feedback vertex? When I say lower bound, I mean lower bound of this nature. Any feedback vertex set on this graph must contain at least these many vertices. And the argument is, but you have to think. Let me see if you can think. Nah. At least I don't see n by 4. You might be able to do it, but I don't see n by 4 at least. I mean, it is possible to show n by 4, possibly, but like it's not obvious. That proof requires a bit more hard work. What was the role of vertex cover? How many objects they needed to kill from the edges? Vertex cover needed to eat up all the edges. Okay. Now feedback vertex set need to eat up how many edges?
One edge on each side.
That's okay, but I do not want that. All I like out of 3n by 2 edges, any feedback vertex set must eat up some set of edges from here. And that, what is that set?
3n by 2 minus n by 2.
minus. So, at least this many the guy need to eat it, no. So, at least any feedback vertex set must eat up at least n by 2 edges, because I mean, you get my point. So, it might sound okay. So, now I still have this bound, no, 3x has to be at least n by 2. So, x is at least n over 6. I am not trying to come up with something very smart. All I am trying to say you that there are some interesting things happening in this graph. Look at, after I delete feedback vertex set, how many edges are left in your graph? So, those feedback vertex set have eaten how many edges at least? Which is at least? So, x has to be at least 3x, because one guy can only eat up 3 edges, right. So, 3x must be greater than or equal to n by 2, no. So, the x which is my feedback vertex set has to be greater than or equal to n over 6, no. That is it. Okay. So, we know that in 3 regular graph, any feedback vertex set has size like linear. I just showed, right, like do not worry about 6, it is like, okay. So, now any FVS has size at least n over 6, and now suppose if this is true, this statement is true, then what does it imply? Can this graph has n divided by log 100 by n vertex disjoint cycle, maximum like. So, now I want a lower bound on max packing, okay. Let us see, right. I mean, otherwise they cannot tie up together, no. Imagine, right, imagine yourself that I say, hey, this graph only, like this 3 regular graph can only have 5 vertex disjoint cycle. Can I say this statement? Look at any 3 regular graph, I say this graph has at most 5 vertex disjoint cycle. Can I say this? Because if I say this, and if this statement is true, what will imply? Then this guy has how many vertices? What it is, the feedback vertex of size how much? Some say there is no big O, for example, say just k log k. Then it will imply 5 log 5. Does it seem possible compared to n? Right? Because any feedback vertex set at least requires n by 6. You get my point? Okay. So, right? So, how many cycles do I need in this kind of graph? So, I want to say any graph or minimum any 3 regular graph contains at least these many vertex disjoint cycles, any. Okay. So, for example, if you notice, right, if I say this graph contains n over log q n cycles, like I say, then what will happen? If there exists any 3 regular graph containing these many, right, then what does this imply? This imply that then it has a feedback vertex set of size how much? N divided by log square n. But I know every 3 regular graph has, look, I am talking asymptotics, I am not talking exact number. It is n by log square n. It is much smaller compared to this. You understand my point? Imagine that there is a 3 regular graph has, say I have a 3 regular graph and it has at most n divided by log square n, say not log square n, let us say log square n vertex disjoint cycle. What will that imply if this statement is true? Then this implies, like, so it has at most this. So, suppose it has strictly less than n by log square n. So, if I put k equal to n divided by log square n, then what happens? This is wrong. So what is true? This is true. If this is true, then it has a feedback vertex set of size how much? Which is equal to, but every tree regular graph has a feedback, so this is impossible, no? So what does it imply? So which implies that even there cannot exist a 3 regular graph, again I am talking asymptotics, which has at most n by log square n. In fact, anything less than this seems stupid, like of course like some constant here, right? So every 3 regular graph contains roughly n divided by big O of log n number of vertex disjoint cycles. Okay. Right. So I want you to see this in the like what is at heart of some of these combinatorial lemma is this kind of push and pull that happens among the combinatorial structure. So how these disjoint cycles are forcing things and the other way around. Okay. Yes.
But isn't that the thing that we're trying to prove?
Yeah, I understand that. Yes, this is exactly.
We are using the same fact to.
I am not proving anything. I am just trying to tell you that if you assume this fact, and I prove one fact independently,
Yes.
okay. If this statement is true and this statement true, what are we trying to prove combinatorially? What are we trying to show? What does it mean? Of course, I will prove this without using this. Of course, I am not proving like this is just some combinatorial fact. So if this statement is true, then all I am telling you, and because we prove this, in any 3 regular graph, there is how many vertex disjoint cycles? At least n divided by some big O of log n number of vertex disjoint cycle, and that's a truth. Okay, that's all that I am saying. Okay, I will prove everything formally, don't worry. Okay, so okay, proof is fairly non-obvious. I mean, it's obvious, but it is non-obvious in a certain sense. Okay. So if this graph is 3 regular, what is the shortest cycle? I am going to apply our method. I already told you a method, no? So I am going to just apply that. Okay, you know, okay. So what did I say? I said, let's pack first small cycle. What is small cycle in this graph? No. I want a provable bound. It's a 3 regular multigraph. It means it always has a cycle of length at most 2 log n. Okay? Okay. So this is 2 log n object. Okay? Now what will I try to do? I said fine, if this is 2 log n, here is my remaining graph. Okay? So here is my remaining graph. I would like to prove, okay? So I want to say this is so whatever I try to prove, assuming, so I know this kind of statement, right? So essentially now I am trying to tell you that look, I am really going to show to you that this graph contains at least that many disjoint cycles. That's all that I want. So whatever I asserted, I want to prove this. So how am I going to prove this? I am saying look at the shortest cycle, let's delete it for now. And if this graph, but unfortunate point is this graph I cannot guarantee that this is 3 regular, because once I delete these vertices there are some damage. There could be some vertex here which has edges here. So these kind of vertices will lose out its degree. So this is no more a 3 regular graph that I can apply the statement which I was talking about. Oh, if a graph is 3 regular or if the minimum degree is 3, then there exists a cycle of 2 log n. I cannot apply some of these. But I want to see that like this damage is very limited, so that I can, you know, like I can handle this. Okay, you get my point, right? So if I try to prove this like writing by hand, it becomes very messy. So how do we go about proving it? You try to prove it using induction. right? So induction on what? Induction. So now, I mean, I want to prove exactly this. So I am saying that if the graph is, if you give me a number k, I said if this 3 regular graph is larger than some threshold of this, then it will contain enough cycles, right? And what will be the threshold? I say, look, if you give me a number k and your graph has more than k log k vertices, more than say order k log k vertices, then you should contain k vertex disjoint cycle. Because what did we saw just now? We said, right? So the relation is like n by log n vertex disjoint cycle in n. So if I say I have n cycles disjoint, so what is the number of vertices I should expect in the graph? N log n, right? So this is what I'm going to do. Says, look, if my graph has, so you give me a number k, if my 3 regular graph has more than say order k log k vertices, then I'm guaranteed that it has k vertex disjoint cycles. Otherwise, okay, so what? So then in those cases we will be done for this. Otherwise, what is the graph? Graph contains how much vertices? At most k log k vertices. Take all of them as your FVS, no? And that's still okay because anyway, now you see, right? They are okay because k log k vertices is trivially FBS, but anyway, every FBS is roughly k log k in those graphs. You get my point? So this is exactly what so the proof idea is very simple. The greedy strategy that we applied. Pick up a cycle, remove it, and keep doing this. But now this number starts coming up. So to handle those numbers, we'll apply induction on k. We say, okay, look, if the graph is large enough, then I will be able to find you k copies of this. Right? Does that make sense to you? Okay. So now let's write down those numbers. Okay. Otherwise, the proof is precisely exactly this. What I wanted to say, look, I have, so what I'm looking at this point of time here. Okay. So I said, look, if the graph is large enough, then I have that many cycles. So what I would, so for example, if I wanted to prove n by log n, I say, let's take out this graph, cycle. This graph is large enough that now I will be able to find the cycles. How many cycles? N divided by log n minus 1. So that I can take those cycles and take this and patch them to get copies, right? So this is exactly the greedy strategy that we employed when we were doing our packing. Delete it and say, oh, inductively find among them. Rather than trying one by one, I could do this. Okay. So that's all that I'm going to try to do. That if the graph is large enough, after I delete this, this graph is still large enough with respect to k minus 1 so that you can find copies of enough objects here. Okay, that's it. So this is the whole proof strategy. Don't ask me for these numbers from there where they come, because they come, if you work it out, they come. Okay, but I mean this is classically these numbers. Okay, okay. So you prove some sk is some number is like 4k times rk if k is greater than or equal to 2. Okay, I will tell you what, 1 if k is less than or equal to 1. Okay, where, what is an rk? What do you think rk should be? Like, it should roughly by like log k, but for the maths to go through, we are going to do log k plus 4. Okay, look, it is, I mean, this looks a scary function, but what is this? Basically, rk is like order log k, no? Right? So it's like, but if you don't take these numbers properly, your base cases will start failing all over the place. Okay, so these are just made to, I'm quite sure if someone takes some other numbers also might be able to work it out. Okay, is that fine? Okay, so what is the lemma I'm going to prove to you is the following. Okay, so the lemma I'm going to prove to you, let k be a natural number and h be a cubic multigraph or cubic 3 regular multigraph, whatever you want to call it. Okay. Now what I want to say, if is greater than sk, okay, if the size of h is larger than this number sk, then h contains k vertex disjoint cycles. Okay? It's not obvious that if I prove this, how do I prove this? We are talking about any graph, any k, and this talks about 3 regular graph. Okay? But there is a connection, and by that I will also give you probably first known constant factor approximation algorithm for feedback vertex set, like olden days, 90. So in those days, designing those algorithms were difficult. Okay? Okay. So proof is by induction on k. K equal to 1, is it obvious? Why it is obvious?
Either it just has one cycle or
Yeah. So all for k equal to 1, all we care about that if you have a cubic graph, it should contain a cycle. It does contain a cycle, right? So this is fine. You get my point? No, right? So for k equal to 1, all I needed to show, what I needed to show, like k equal to 1, if h is greater than or equal to 1, then h contains k. But h is a cubic multigraph, right? So irrespective of whatever maybe its size is, this contains a cycle, right? So for k equal to 1, all about h has a cycle, and this follows from h being 3 regular or cubic multigraph. Okay? Okay. So okay. Now let C be a shortest cycle in G. Okay. And why I am finding shortest cycle? Because on this we do have an upper bound. Okay. Okay, but like let C be a shortest cycle in G. So now here is my C, and here is my remaining V minus C. Okay. Okay. So now let's look at V1. I call this partition V1, and the remaining is like V2 for now. Okay. Now let's look at the vertices here. Tell me how many edges are crossing. How many, at most, how many edges could cross from between this and this? So that is upper bounded. So hence it is upper bounded by
size of V.
or cardinality of C. Okay. Okay. So in the beginning, look at the edges that are going across. Every vertex, this is basically a cycle, right? Right? And if everybody has, right? And it's a shortest cycle, so it's not even fine. So everyone has at most one edge going out like this. Okay. So the number of crossing edges is upper bounded by C. Let's call that some M. I don't know. Let's say C. I mean, I do not want to use some, otherwise it'll just confuse. Okay. So now I want to do some operation. Look at a vertex here, whose degree is 0 in graph induced on V2. Some V in V2 such that degree of V is 0 in graph induced on V2. What is the meaning of this vertex then? Where are its all edges? So all its edges are going across. Okay. So you tell me, if I wanted to do induction and do cycle, is this vertex useful for me? They are not useful for me, right? So I rather move this there. Okay, but now you can say, oh, but how many times will you do this operation? But when I move this, what happens? When I move this vertex here, what will happen? What happens? Number of crossing edges drops. strictly drops, because when I move here, nothing new is coming up, no? So that's fine, okay? Okay, so when I move this operation, when I do this operation, okay, this is bad. Move V to V1, okay? So what is the, what happens now? Okay, so what happens now? V1 becomes V1 union V, and V2 becomes V2 minus V, okay? And what else happens? Crossing edges strictly decreases. Okay, that's great. Then as what else can I say when it will drop? Okay, then there's nothing about degree 0, right? Even if the vertex had degree 1 here, I would be good. Look at this vertex, it has a degree 1 here, it has a degree 2 here. What happens if I move here?
Number of crossing edges
Still decrease, right? Because 2 becomes this and 1 becomes crossing, okay? So until a vertex has degree at most 1 here, this operation can be applied, okay? So why say? So what we'll say? While there exists a vertex V in V1 such that V has degree at most 1 in V2, do this operation. So in V1, now after this process, what is the size of V1? After the end of the process, size of V1 is upper bounded by C plus at most C, right? Because each time you decrease this number of edges, right? So this operation can only happen at most the number of crossing edges that we started with, which is upper bounded by cardinality of C, right? Okay. Okay. So what is the property of graph induced on V2 now? There are some beautiful things happening. What is the property of graph induced on V2? So minimum degree is at least 2. That's all that it is. Okay? But how many vertices are of this nature? That is also bounded in some sense. Okay, tell me.
This degree 0 vertex that we are moving,
Hmm.
if there is at least one degree 0 vertex of such kind,
Huh.
then there cannot be any degree 1 vertex.
I didn't get your point.
Because like, if there is a degree 0 vertex which is all 3 edges going to C,
Yes?
then there cannot be any degree 1 vertex of such kind.
Why?
Because this thing all like otherwise create a shortest cycle. Like, if the cycle length is more than 5, then
Yes,
there
yes,
is
I know. But this is not important for the proof, so let's not go into the details. That this operation only will happen 3 times. Okay? But I'm not going there. Okay, this operation cannot happen more than this because then you will get a shorter cycle. But I don't want to go there. Like, why? Like, okay, I'm happy to lose a constant and not going into this like tiniest of detail. Okay? So I have eaten of that. Okay? But I'm fine with this. This you agree?
Sir, can you repeat how size of V1 is less than or equal to C plus C?
I started with size of V1 as equal to,
Mod C.
correct. I did one operation. Size increased by 1.
All the yeah.
No, I just moved one vertex.
Yeah.
Every time I do, I make only one vertex, right? So at the end of this, and how many times have you applied this operation? At most cardinality C times, no?
Why is that?
Because every time the number of edges decreases here. How many number of edges are there between C and V minus C? This every vertex a degree exactly equal to 3.
Yeah.
And this is a cycle. So for every vertex, 2 edges are already taken. So there's only 1 edge going out, no? That's fine. Okay. That's good. Okay.
So, can it happen that when we take a vertex from V2 to V1, can it happen that in C, we can create a cycle smaller than C?
Yeah. I mean, because C is a shortest cycle, you shouldn't create. That is why this operation is actually you cannot do more than 3 times. But like I do not want to do this 2-page proof. Like it is, I mean, you can prove for yourself that yes, it can create, and this is why you can actually prove that the number of times this subroutine can be applied is upper bounded by 3. Just 3. Okay? But like, if it is not enriching our proof, like, should we go there? Like, when you are writing a proof, no, there are some interesting facts and there are some non-interesting facts. So, it's important to not worry about those non-interesting facts unless you require them for proving. So, structure can give you many things, but the proof, not all the structures are important. Okay? So, just you should leave them, otherwise proof will, otherwise you start thinking unnecessary. Like, what is my goal at this point of time? What is my goal? Let's try to understand what is my goal. My goal is the only one thing. I am only removing vertices which are useless, right? If I look at a graph induced on V2, I could have applied the following reduction rule also, right? What is my reduction rule? Remove vertices of degree at most 1. But I want to count how many such operations I am doing, because as many operations I am doing, this number of vertices in V minus C is decreasing, and I do not want V minus C to decrease, right? Because those are in any way not part of cycle, so I have forgotten. But now, so that's all that I am saying. I am just applying degree at most 1 rule. But now look at this, because if I was doing my greedy algorithm, I would have removed V1, right? And these vertices, and now I also want to have some measure on how many degree 2 vertices are there. How many degree 2 vertices are there? There is no log n business. Talk in terms of why? Why it is a degree 2? Because it has a crossing edges, right? Because it has a crossing edges, right? So how many crossing edges are going after this operation? At like you started with mod C crossing edges, every time it only decreases. Maybe you never applied this process, if you, which is what is going to happen most times, right? Which implies that the number of vertices which will have degree 2, okay? So, okay, let A be the vertices of degree 2 in graph induced on V2. This is upper bounded by cardinality C. Why? Because each such vertex has an edge in V1, and such edge is upper bounded by cardinality C. That's why. Okay. So what do I know? That's great. Now what do operations I know? I can short circuit degree 2. Okay, and that, so now I want, so if I want to apply induction, what do I need to do? I have to come up with a cubic multigraph. So to come up with a, so why did I did this all this? Because on this graph I wanted to apply induction. If I wanted to do induction, I need to clean it up. What is the meaning of need to clean up? Remove all vertices of degree up to 2. So 0, 1, I just threw them into this, I had a bound on them. 2, I still have bound on them. So now what I can do? I said just, because now if you give me a k copies here, I can still undo this, and those will form vertex disjoint cycles, and take this cycle, and that will give me a k vertex disjoint cycle in the original graph. Okay. So what is my multigraph that I am going to construct from here? Okay. Okay, so I will leave you a hard job for you people, because those are not fun. Here it is, no? So what is my H? Look at H prime is what do you call? Suppress degree 2 vertices in graph induced on V2. That's H prime. What is the meaning of this? So you have a degree 2 vertices, right? Say x, y, z with 2 degree 2 vertices. You just short circuit it. What you do? You basically x and z, you make a edge between them and delete y. Now this is why I am assuming that the graph is a multigraph, because it's possible that I have an edge already between y and j. So when I x and z. So when I do this, I get a multi edges, right? So that is why I am assuming in the beginning itself that my statement is even true with respect to multi-graph, otherwise I don't know how to do this. Okay. So, this is the H prime that I want to work with. Okay. So, what is the size of H prime? Is at least equal to how much? Please tell me. Minus how much?
H minus C.
Hmm? No. It's also, look, if I do obvious, you will say, hey, cardinality of V is bounded by 2C, right? And there is a degree 2 A bounded by C, so it's like 3C, right? But that's not right bound. Say, tell me why. Can I replace it with 2? I want to replace it with 2. Because look, either you add a vertex or you add to degree 2. You get my point? Look, if you moved here, then the number of edges becomes how much? C minus 1. Look, what is the cardinality of A? Cardinality of, okay, look at this. What is happening here? Okay. So, in the beginning, I have how many edges here? C edges. Okay. So, if I made this move here, C decross to how much? C minus 1, right? Then at that point of time, so what is the cardinality of A? Actually, is upper bounded by C minus 1, right? It is at the end, how many crossing edges are going on? That is what it is bounded by. So, if I apply this operation twice, 2 goes in, then number of crossing edges decreases. So, the total number of object is degree 2 vertices here plus the number of operations I have done, right. So, this is why you can do 2 here, okay. I mean, even with 3 it's okay, I mean if you want it, but like the way the numbers are, otherwise you will have to increase some number by somewhere. So, what is my goal now? What do I need to show now? If I wanted to apply induction hypothesis, what I need to show? All I have to show that the H prime, which is this, should be greater than or equal to Sk minus 1. If I show this Sk minus 1 by induction hypothesis, this is all true and I am done. So, what is left now to do? To do some stupid ugly maths, which I will not do it. Okay? This is literally some computation which is, I don't think it's very useful to do in the class. Right? I wrote you a function, right? Okay. Is that meaningful now? Okay. Okay, so I still have some 10 minutes. Let me use that to suppose if this statement was true. Okay. So, please read dstar and do the computation. Okay. This is like, it's like, okay, fine, this is like this minus this, so this is like, but the numbers are chosen in a way that this maths will hold. Okay. So, I do not want to do that part, but it is exactly what we have been doing even for our this greedy packing business. It's like now we need to be a bit more careful, but suppose if I prove this carefully, how we go about, like how does it imply whatever we wanted to prove? So, let me give you that proof in 10 minutes, like idea of the proof, and then next time we will spend first 10-15 minutes making it formal. Okay. So, let me give you an idea how do we go about it. Let me just take this phone. Okay. So, now what I want to show? So, I want to show formally that f of k vertices meeting all these cycles. So, you know how do we go about proving it? It's a very beautiful thing, and now I will show you what we proved earlier gives a constant factor approximation. That we did this now maths, right? Oh, if the 3 regular graph is there, then you at least need n by something, right? That will give you a constant factor approximation. Okay, that's simple fact. Okay, it will not give you 4 or something, it will give you some constant factor, and if you do that tight analysis, it will give you factor 4 approximation. Okay, so I'm going to rub this. Okay, I hope you understood the whole process. Okay. So now how does the proof goes? So I said, okay, fine. So if I have to apply this, if I have to start with general graph, what I have to do? I have to find this object. So how do I find this object? Okay. So I greedily find this object. What I do? I greedily find this object. So I have a graph G. I find a subgraph H. So what is subgraph? And what is the property of this? It's a very nice property. This is a maximal subgraph of G where every vertex has degree either 2 or 3. You now say, why such a subgraph even exist? Make this greedy. How will I start with making this subgraph greedy? Start with a cycle. No, it's a subgraph. I'm not talking about induced subgraph. I'm just talking about subgraph. I start with cycle. Keep adding this. If I can add an edge without like or path or something, then I just keep adding this, right? So it's like it feels very non-trivial that why should such objects exist, but if you think for a minute, right, it's not that, right? So I can greedily find this. Look, let H be any maximal subgraph. So in particular the one which I can find greedily. How can I find? I first find edge like vertex disjoint cycles. I found. Edge meaning greedily. I don't care about length, no, I found. So here's one procedure to find this. Okay, I find a cycle, remove those set of it. Okay, now I put, but now it is this, right? So now what I say, look, I ask myself, is it, so of course this piece has no cycles, right? If I look at, but now, so there are some vertices here, okay? But now I needed to, I'm going to add something. I will say, okay, fine. Is there a vertex here and a vertex here? Like, is there a degree 2 vertex such that there is a path between them, okay? That does not uses any, like, is there a path between them which is like this? And when I say you should think not with vertex, you should think with respect to, yeah, I mean that's also fine. So for example, what will happen? If I have a, so this also should allow you to have, suppose I have 2 degree 2 vertices here and there is an edge between them at that edge, because that's a path length of degree 0 where every internal vertex is from outside. So I allow such thing, but only between 2 degree 2 vertices. If, so what is my procedure? Add a path between 2 degree 2 vertices, add 2 degree 2 vertices in my current subgraph, vertices in my current subgraph, okay, where all internal vertices are here, are outside my initial cycle. Okay. Okay. So I keep doing this. So I will get an H which has this. Now I cannot add this. Okay. Okay. So I cannot add this anymore. So let's look at amazing property of this graph now. Okay. So here's my H which is a subgraph. Okay. Now look at V2, V3 here. What is this? Vertices of degree 2 and this is vertices of degree 3. Okay. Is that fine? Okay. Now ask yourself, now let's look at G minus V3. So I deleted this set of vertices first. Look at this. Okay. Now ask yourself, is there 2 degree 2 vertices here which has a path between them that does not uses like this degree 2 vertices. Can there be such a path? Then that will contradict the fact that what you had is a maximal, right. So, between 2 degree 2 vertices in my H, there is no path. Okay, excellent. Okay. Or rather, let us say delete degree 3 vertices from my graph, okay, and ask where are my cycles? Where are my cycles? Right. So look at look at any cycle in my graph, where it is going to contain. It is only with all respect to all degree 2 vertices only in my this, right. So like either you are going to so now look at any cycle here. Now look at any cycle here, right. So look at any cycle, suppose in G minus V3 I have a cycle here. So either it is going to, and look, first notice one thing, that this cycle must contain at least 1 degree 2 vertex that you have picked up, because otherwise your solution, otherwise your H was not maximal. And anyway, how did we make? Looked at all this, okay. But now notice, look at this guy, okay. Now ask yourself, can this cycle contain 2 degree 2 vertices, let us say, or at least 2 degree 2 vertices which we have chosen? No, because if it contain 2, look at the internal vertices, right. It does not contain degree 3 vertices, because, so what are these vertices? Those which is in V minus V2 union V3. But then why did you not add this path? This is a degree 2 vertex, this is you could have added this path in your H, but you did not add it. So such cycles do not exist, first of all. So what is this? Every cycle after that had some interesting property. What is that interesting property? They are just like every cycle after that is just hanging from here, like some degree 2 vertices. Every cycle after I delete a degree 3 vertices can be characterized by with whom you are hanging. You get my point? Okay. Okay. So let us talk about vertices that they are hanging with respect to 2 vertex V1 and V2. Look at these 2 vertices which they are hanging. Okay. Now I ask myself, there is a cycle that is hanging from V1, there is a cycle that is hanging on V2, can they intersect? If they intersect here, then there is a path. That does not happen. So every guy has bunch of cycles that they are pairwise disjoint. So how many such vertices can be there? Either if these are more than k, then I will say, here is your k vertex disjoint cycle, done. Otherwise, if I take these k minus 1 vertices and V3, we are done. Agreed? So that forms a feedback vertex set. What forms a vertex? V3 and these vertices of degree 2 in my H, where these guys are bunched together. That forms a psi. Okay, excellent. Now look at this H. Now suppress these guys, like degree 2 vertices in H. What is this graph now? It's a 3 regular multigraph. Either its size is more than this, because when I suppress it, it's a graph on degree 3 vertices, precisely V3. If this number is large, what happens? If it is more than k log k, then this subgraph itself contains k vertex disjoint cycle, I am still done. So this size is small. How much is small? It is at most k log k. So what did I find? Take this k log k vertices, take this k minus 1 vertices, and you are done. That's your feedback vertex. Okay. Now how will I get a constant factor approximation? Okay. Look at all this degree 2. So for each of them, I have a pick up all this, but for each of these cycles you are picking up something, no? What are you picking up? You are picking up, you have a disjoint cycle, so you have to pay one here, one here, one here. So this is less than equal to opt, where opt is FVS, because FVS is more than this, right? Now look at your degree 3 graph, regular graph, right? If I make this multi-graph, what do I know? Any FVS has to contain all the vertices, no? At least n by 6. So you picked up all this guys, picked up this, so it's a factor 6 approximation, no? Because with respect to FVS for 3 regular multigraph, we said every FVS must contain at least n by 6 vertices. So in particular, you take all the vertices from here, right? So you would have chosen at most 6. Why? Because this is a subgraph of my graph, right? If you have a FVS of size at some opt, it must kill all these cycles also, right? So opt like with respect to these vertices, opt has to be at least greater than equal to n prime by 6, where n prime is size of this, right? So that will give you factor 6 approximation. So this is how you can play around with, and if you play much more nicely, you can get a factor 4 approximation. If I did not do this stupid 9 by 6, but I did something more smarter. Okay, so this is what we will do next time, right? We'll try to formally prove this thing, but this is our whole overall idea. So what did we do? We started with G, maximal degree 2, 3 subgraph, deleted degree 3, then this 2, 3 subgraph had amazingly beautiful property that now every cycle are like just hanging from here, like, and you can actually prove that even the 2 cycle that they are hanging, they also do not intersect. So it's like a flower, because if they hanged, then you could have added something more. Okay, so like there are some amazingly beautiful property that they are holding here. Okay, so you could have picked up some other degree, because what will happen if you have this and you have this, right? And if there is some other cycle that they intersect somewhere, so you can take this and form a cycle. That's a contradiction to the fact that you had some other cycle. So you can do many things. So, but that is not required. So this H has lots and lots of beautiful properties. So what I expect you to do today is go back, please do the maths, okay? And the next class, either on Monday or Tuesday, I will do the formal proof for Erdos Posa theorem. Okay, that's all.